All right, Trig, this is section 3.2, exponential functions. It's mainly talking about the graphs of exponential functions. We should be able to get through these notes today. They're not too terribly long. There's a couple story problems, so get your calculators out, but it's really not that bad of a section. Here's the homework assignment for it. Okay, there's a couple graphing things, but I'll show you some shortcuts to take. Okay, so first things first, exponential functions, they're differentiating between what is exponential and what's not exponential for a function. These are all considered exponential functions. Let's talk about them really quick. The thing that you want to make sure and note is that the variable is in the exponent for an exponential function, okay? Then this number is something called the base. And what you want to pay attention to is that number a number that's bigger than 1 or a number that's less than 1? It's not that it's a fraction or not a fraction, because like 4 over 3 is a fraction, but that number is bigger than 1. So it is a growth if the number is bigger than 1. So like this is an exponential growth function. Okay? Growth functions on a graph look like this. They are growing exponentially. Okay? This function, 1/3, is his base number. He is going to be what's called a decay function, or sometimes they'll call it a depreciation function, okay? A depreciation or a decay function is going to be the same, but he's going to go this direction. Now, each one of these functions is going to cross at the value of 1. 1 is the y-intercept always, unless we move him up, down, left, or right, which I'll show you here in a second. And I'll show you why it crosses at 1 here also, okay? The square root of 2 is my base number, and the square root of 2 is like 1.41 ... whatever. So that makes him a growth function. So he is going to look like this again, okay? Those are exponential functions. These are not exponential functions. This guy is x to the second power. So the variable is in the base, and this is called a polynomial. This is a quadratic function. So he's a parabola, basically, okay? This guy is not considered an exponential function because the base is negative. All right, so you have to be really careful. There's kind of a weird thing going on there. I don't know. I have always said that these were technically exponential functions where he's reflected, like he's flipped. I don't know, this makes him flipped across the y-axis, but whatever. They're saying that it's not an exponential function. I don't know. If the base number is 1, right, like over here it says if it's greater than 1, it's a growth. If it's less than 1, it's a decay. If the base number is 1, this is not going to be a exponential function at all, because whatever number you plug in for x here, like 1 to the second power is 1, 1 to the third power is 1. So basically this is a constant function at 1. Like it doesn't matter what value I plug in for x, the y value is always going to be 1. So that is not an exponential function, okay? So exponential functions, non-exponential functions, whatever, okay? All right, every exponential function has a place where he crosses, and it is going to be at the value of 1 so he's going to touch there always, okay, until we move him up, down, left, right, which I'll show you looks like in a second, like this. Doing this and this to him is going to move him up, down, left, right. That's going to change him just slightly, but every function that's like just the base and the exponent is going to cross at 1, because if I plug 0 in, like 0 comma something, right, 2 to the 0 power is 1. Anything to the 0 power is 1. So 0 comma 1, that's this coordinate point right here. Okay, so he's going to cross at 1. Same thing over here. If I take 1/2 to the 0 power, that's going to be the coordinate 0 comma 1. 1/2 to the 0 power is 1. So he is also going to cross at 1 right here. I'm going to put a dot there. Okay, this guy is going to be a growth function. So I'm going to plug in, like, let's say we plug into the first power and to the second power and to the third power, okay? 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, right? So I have those coordinate points. I have 1 comma 2. I have 2 comma 4. I have 3 comma 8, and he's going to be like this over here, okay? Now, if I go back the other direction, okay, follow along really carefully. If, let's say I go -1 and -2 and -3, right? Okay. All right, let's talk about what 2 to the negative first power means, right? If you have a negative exponent and you're trying to get rid of it, you flip him to the bottom. So this is like over 1 if I make it into a fraction. If I want to get rid of that negative exponent, he will become 1 over 2 to the positive first power. or just 1/2. Okay, this guy, if I do him to the -2 power, this will be 1 over 2 to the +2 power, which is 1/4, right? If I do to the -3 power, this will be 1 over 2 to the +3 power, right? Like that exponent just goes down, like he just becomes a positive exponent when he goes to the denominator, so this will be 1/8, right? So -1, comma 1/2 will be there. -2, comma 1/4, -3, comma 1/8, and it'll just keep flatlining. But it will just kind of flatline, and he will have what's called a horizontal asymptote. We've talked about those before. He'll have a horizontal asymptote at 0. Okay, so that's how that works. Okay, again, every function will cross here at 1 and have a horizontal asymptote there at 0. Okay, until we move him up, down, left, right. Okay, same thing here. 1/2 to the 0 power is 1. If I plug in 1, I plug in 2, I plug in 3, whatever, okay? 1/2 to the first power is 1/2. 1/2 to the second power. This is like saying 1/2 times 1/2. That's what it means to take something to the second power. 1/2 times 1/2 is 1/4. If I take it to the third power, that means I'm multiplying him by himself a third time, right? A third time. 1/2 times 1/2 times 1/2 is 1/8, right? So it's kind of like the opposite of these guys, right? Okay, now let's look at negative. Oh, let's plot those. 1 is at 1/2. 2 is at 1/4. 3 is at 1/8. So he's going like this. He's flatlining the other direction, right? So I'm going to guess that he's going to do this on that end, but let's check that, okay? So let's say I plug in -1, comma something, -2, comma something, -3, comma something, right? Okay, so if I have 1/2 to the negative first power, what I want to do is I want to like get rid of the negative exponent by like moving him to the bottom. Well, he's got a top and a bottom. So what I can do is I can just flip-flop these two, and this becomes 2 over 1 to the first power, which is just 2, okay? If I do that 1/2 to the -2 power, this is like 2 over 1 to the +2 power, okay? Which is just like 2 to the second power, which is 4, right? 1/2 to the -3rd power is like 2 over 1 to the +3rd power, which is 2 to the 3rd, which is 8, right? So it's kind of the opposite of what we did over here. -1 is at 2, -2 is at 4, and then we have it like all the way at 8, blah, blah, blah. So he looks like this, right? So this is an exponential decay function, decay, and this is an exponential growth function. And again, it has to do with that base number. If the base number is bigger than 1, it's a growth. If it's less than 1, it's a decay. Cool. That's my exponential functions. Good. Oh, he has a horizontal asymptote, as they all do, right? Okay, that's just graphing an exponential function. Cool. That showed you like what all this stuff is. This is all what the graphs of exponential functions look like. So again, it crosses at 0, has a horizontal asymptote, blah, blah, blah. If the base number is bigger than 1, if the base number is less than 1, but greater than 0. I didn't put that in there. It has to be greater than 0, but less than 1, okay? Because you can't have a negative base number because they don't call it an exponential function if it's a negative base number. Okay, that was a lot of stuff. I just talked really fast. Sorry. Okay, let's go down here and let's talk about what these things mean. So, let's say I'm going to write some stuff down up here at the top. Y equals, let's say I have 2 to the x power. I'm going to write them like that, okay? I'm going to say minus a number, I'm going to say plus a number, and then I'm going to do negative. This guy is going to put him over the x-axis. This number is going to move him left or right. I'm going to say opposite sign. So negative actually means to the right, positive means to the left. This guy moves him up or down. Okay, and I think for now that's all they're going to have you do for exponential functions. We're not going to worry about vertical stretch, compression, anything like that, okay? So, yeah, write that part down. That's what those numbers are going to do to this, okay? So, first things first, when we're doing example 2, let's talk about what the parent function is, okay? Because if I strip away all the numbers, okay, 3 is technically not a number that's involved in moving him around. 3 is a part of the parent function. 3 to the x power is my parent. Y equals 3 to the x. Okay, so then I have to figure out what is it a -2 or a +2? Come on. minus 2. I have to figure out what the minus 2 is doing, and I have to figure out what the plus 4 is doing, okay? Now, technically in the order of operations, the minus 2 is doing first, because if I were to plug a number in here for x, I would subtract the 2 before I add the 4. So the minus 2 is moving him to the right 2, and the plus 4 is moving him up 4. Okay, so here's how you can cheat by graphing this. I'm going to do this. Normally, he touches here at 1. He touches here at 1, and he has a horizontal asymptote there, like that, okay? But if I move him to the right 2, 1, 2, that means my dot of intersection is going to go to that spot, and I have a horizontal asymptote there. But also, if I move him up 4, 1, 2, 3, 4, now my horizontal asymptote's not here, it's here at 4, and my dot is going to be there where he intersects. So before he was here, if I go to the right 2 and up 4, it's going to move my dot to that spot where he's going to intersect, okay? And he's going to be an exponential growth, so he's going to look something like this, right? Ish, okay? If you want to, like, have your units specifically, 3 to the x power is going to, so he's intersecting here at 1, right? That means the number that's just to the right of this guy is going to be at 3, or 3 above, I guess. This is at 1, so this guy will be at 3. So 1, 2, 3 above, that's where he will be. If I go over 2, he'll be at 9 above, where your horizontal asymptote is, okay? So that was a lot, but if you want points specifically, for me, if you just have the general shape and you know where this point is located, if you have your horizontal asymptote and this point is in the right spot, that's good enough for me. But if you want points exactly, just know that, like, if you go 1 over from where your intersection point was at, 1 over, he'll be up at 3, or 3 above. If you go 2 over, he'll be up at 9, because 3 squared is 9, 9 units above. You can always plug in numbers in for x if you want to get points specifically as well. But there is what the graph is going to look like, okay? All right, next thing, we're talking about e. Okay, E is a number that naturally occurs when you are doing compound interest, okay? So one of the formulas that we have for compounding interest, when we dumb it down, is A equals 1 plus 1 over x to the x power. Really, compounding interest looks like this. P times 1 plus 1 over n, no, r over n, to the nt power, okay? So basically, they've taken this and dumbed this down a little bit. I don't have a p-value in here, which means 1 or $1 is my p-value that I'm starting with. And then they're just representing, like, my interest rate is 1. N and t, they've kind of lumped together to be x's. But anyway, they are saying that in the most basic format of this compound interest formula, this number, the larger x gets, so like maybe x is 100, and maybe the next time x is 1,000, and maybe the next time x is 1,000,000. As that number increases, this whole entire value approaches the number 2.7182818, blah, 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 and that is the number e. Okay, it's a number that, like, naturally occurs in compounding interest. It's kind of like how pi naturally occurs when you're calculating area and circumference of circles. It's just a number in nature, whatever, that is like something that it conforms to, okay? So over time, that number is going to approach a value of e, okay? If you want me to elaborate that on more when I come back to school, I sure can, but that was, like, dulled down a little bit, all right? Now, e to the x power is still an exponential function. It's just like, think of it, 2.718, blah, 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 to the x power, okay? But it's still, when we graph it, it's still going to cross here at 1. So I'm going to have an intersection there. It's still going to have a horizontal asymptote, okay? It's just that when I go over 1, and I plug 1 in for x, my next point up is going to be at 2.7, okay? So right about there, and that's what he's going to, like, look like, I guess. The larger your base number is, the steeper this is right here. So if it's like to the, I don't know, 1.1 power, right? He's going to be like really wide and narrow, or right, wide and long. Okay, but if it's to like let's say 7 to the x power, it's going to be really steep. Okay, so that's just how that base number is going to determine your function. Okay, so 2.718, just think of that as e to the x power 2.718 to the whatever power, and that's what your exponential function is going to look like. Still going to cross at 1, still going to have a horizontal asymptote. There is that. All right, let's do some story problems. So I just gave you this formula right here. Circle these things, or put some information right next to this. This is the formula for simple interest. Write that as off to the side. They might interest. Simple interest. Yeah, simple interest. Okay, this is the formula that you use. I is interest, P is principal, rate, time. Okay, this one is compound interest. I'll actually write the word out. Compound interest. Okay, and this is the after amount. I usually say principal, rate, time. N is the number of times you are compounding. Okay, so if they say that you are compounding annually, your N is 1. If you are compounding quarterly, your N is 4, because there's 4 quarters in a year. Compounding monthly is 12. Compounding daily is 365. I know that there's a leap year, right? Which technically means that like every year has 365.25 days in it. But we're only going 365 even if it is a leap year. It's a leap year this year. Next month is a leap year month day. Whatever. So we still only do 365. It's for compounding daily. So that's what your N is determined by. Then this one is continuous compounding, which means that if you would compound every millisecond or whatever, this is the value that it would approach, because like the larger this number gets, right? If x was in this spot and x was in this spot, the larger that value of x gets, the closer it approaches e. So continuous compounding, they represent it as, I call this PERT. That's what it looks like, right, in the formula. So continuous compounding is PERT. A equals PE to the RT power. So those are just the formulas that you use depending on what kind of compound interest you are dealing with. All right, example 4, here we go. We might do like, let's do quarterly, and let's do these 3. Compounded quarterly, compounded daily, and compounded continuously. Determine the total amount after 10 years. That's my time. Okay, suppose that 5,000, that's your principal. 6.5%, that is your rate, except I'm going to write in here 6.5%, you have to convert it to a decimal first, so it's 0.065 per year under the following compound options. Okay, so I'm just going to do B, D, and E. B is compounded quarterly. Here's what it looks like if I compound quarterly. A equals principal 5,000 times 1 plus 0.065 over N, and N is quarterly, so N is 4, to the NT power, which is 4 times 10. Okay, cool. You can do this bit by bit if you want to, like if you have a really dumb calculator and you don't trust it and you want to do this in pieces. This guy divided is 0.01625, which means this whole thing is 1.01625, okay? And then I can take that to the 40th power, right? To the 40th power. I'm doing this on my phone calculator, by the way. I don't recommend doing that. And then I take that times the 5,000. So quarterly, this will turn into 9,527, and we go to 2 decimal places because we're dealing with money. So it turns into $9,500, something like that, okay? If we compound daily, I'll go to a different color. This is part D, daily. The only thing that's going to change is that 1 plus 0.065, we're dividing by 365 for daily, and then we take 365 times 10 up here. So that number, your N value, will just change. Okay, so I'm going to start with this divided 0.065. You type this in however you want. Divided by 365 plus 1. I'm going to take that to the 3650 power, and I'm going to take that times 5,000. And I got just slightly more. The more times you compound it, the more money you will get. So that's what it will round to. So slightly more money, okay? Now, if I'm compounding continuously, I think you're going to end up with more money yet or less money. If you said more money yet, you are right. The continuous compounding formula makes it a little bit easier. P e to the r t power, okay? All right, if you want to do some stuff in your head, times 10, you're just moving the decimal one place. So this whole thing would just be 0.65 if you want to, like, make it a little bit easier. All right, I've got e to the 0.65 times 5,000. Less to type in even. Ooh, I get 9577.70. So these two are very, very, very similar to each other because compounding daily is like compounding quite frequently already. So continuous compounding is just only slightly higher than that, okay? But this is the most money I would get, like that's going to be the highest value out of all of these. You're going to get the most interest by doing compounding continuously. So there's that. All right, that was example 4. Okay. All right, last thing, some uses for exponential functions and applications. You will have a homework problem that talks about population growth. So they give you the equation for like how the population is growing. It's going to be a growth function. So y equals b to the x power, where this is going to be some number that's larger than 1. It's going to look something like that. And then you can plug in numbers in for x for values of time to determine what your population is going to be. Growth of an investment, we just saw that under compound interest, is another exponential function. We're going to do an example of this one, the mass of radioactive substance. We're doing half-life. You guys have probably heard that in science class. So half-life examples, that's going to be like example 5. And then temperature of a cup of coffee decreases exponentially. So if I'm talking about like setting a cup of coffee on a table, it might be like, I don't know how hot those get, like 120 degrees. I don't know, maybe that's not very hot. I don't know. 120 degrees, and then it's like it's going to do one of these actually. And it's going to go like this. Now, what's interesting, though, is that for a cup of coffee, your horizontal asymptote is not going to be 0. Probably. It's going to be up here at, they call the ambient temperature, which is the temperature of the room. So, like, let's say your room is 70 degrees. I don't know. It is going to level off at that 70-degree temperature. So, it's going to drop in temperature really fast until it levels out at 70 degrees-ish. Okay? So it's not going to go all the way down to 0. Obviously, your cup of coffee is going to like reach room temperature, not 0 degrees all the way down here, unless your room is 0 degrees, right? So that's how that works. All right. So that's another decay. These are examples of decays. These are examples of growths, unless your population is decaying, but or your investment is decaying. I hope not. But anyway, so typically that's what happens. All right. Let's do example 5. I'll quit talking. All right. Half-life of radium-226 is this many years. Okay, that means it takes 1,620 years for it to split in half. So basically, if you have 10 grams of radium-226, it will take 1,620 years for it to decay to 5 grams. Then it will take 1,620 years to decay to 2.5 grams. Then half of that is 1.25 grams. Then half of that is 0.625 grams. You see how it's splitting in half, and it's taking that many years for it to split in half, split in half, split in half. So it's doing something like this, right? Okay, how much radium will be present after this many years? Okay, all right. How much? Having 1 gram of radium. That's what I'm confused about. Okay, we are starting with 1 gram of radium. I wish they would have put that in here. So this is the function for half-life, except your p-value is right here. Now, they did not put a p-value in there because 1 is my p-value. So they skipped over that, which I get. Like, the 1 is not doing anything. But just keep in mind that, like, in your compound interest formula, actually the formula for compound interest, or for half-life, is your after amount is going to be p times 1/2 and they say the time that you have over, sometimes they'll call it K, sometimes they'll call it H. Let's call it H, where H represents what the half-life is. So the half-life is 1,620 years. That's what they've plugged in for H. So keep in mind that your principal is there, but in this case, it's only 1. Okay, so there's that. All right, now I'm going to take a guess at part A, not a guess, an educated guess. If I plug 1620 in for here, all I'm doing is splitting it in half once, right? So 1 gram, if I split it entirely in half, is going to become 0.5 grams. If you want to plug that into your calculator, you sure can, but that's what you're going to get. This one, in 3240 years, that is halving it twice. So 1 gram became 0.5 grams, then it's going to split in half again, so it's going to become 0.25 grams, or a quarter of a gram. That's what he will look like. Okay, 4860 is, they went in intervals. That's 3 splittings in half. Well, that was kind of anticlimactic. That's not very much fun. This is splitting in half 3 times. So your 0.25 then is going to split in half, right? So it's going to be 0.125 grams, okay? Let's actually plug that in and see what we get, right? So if you don't trust that's like splitting in half 3 years, or you can't see that 4860 is 1620 times 3, right? What you're going to do is you're just going to plug it in. So A equals 1/2, again, the P out there is 1, 4860 divided by 1620, okay? So all this is this stuff. If you divide it, you should get 3. So I'm taking 1/2 to the 3rd power, which is 1/8, or 0.125 grams. Okay, so you can plug that into your calculator as well if you want to. But there is that. Okay, that was a lot. So that's all I have. I'm gonna quit talking and leave you alone. Okay, goodbye.